Previously, we mentioned how the pooling and convolutional layers can be used for feature extraction. Detecting meaningful features given a bunch of images and labels is no easy task, which is why convolutional layers are key players in a convolutional network. You saw how the first filters are trained to detect simple features, and as the first filters build on top of one another, they start to detect much higher level shapes. Looking at the following kernels, how does the neural network learn to start detecting faces? Well, it doesn't. Convolutional networks don't actually know what a face is, but by encountering and seeing a lot of faces in the training images, it learns to start detecting these faces as a meaningful feature. Having detected the required features, now you need a classifier to assign a probability for the input image belonging to some class. This neural network in particular is trained on grayscale images of various breast lesions. What it does is first it extracts the necessary features in the convolutional and pooling layers, and subsequently the output from the convolutional and pooling operations. Each feature map must be flattened into a one-dimensional array of pixels for it to be fed into the input layer of the fully connected network, where each pixel corresponds to a node in the input layer. The fully connected neural network is responsible in taking these features as inputs, processing them to obtain a final probability as to which class the image belongs to. In this case, the input is classified as corresponding to a malignant breast lesion. With that being said, now we know the second part of a convolutional neural network is in charge of classification. The first part is in charge of feature extraction, the second part, classification. The fully connected layers work the same way as the multi-layered perceptron-based neural networks that we've used and encountered all throughout this course, where every node in the preceding layer is connected to every node in the subsequent layer. This is what separates it from the convolutional layer. Each neuron is connected to all the neurons in the previous layer, and each connection has its own weight. Okay, now suppose this neural network was already perfectly trained and it predicted this image correctly according to its label. It is indeed malignant. Now, how does the overall training process work? Well, for the fully connected layer, since ultimately it's just a multi-layered perceptron network, it simply updates its weights and bias values to minimize the total error function based on a gradient descent algorithm. First, like always, random values are initialized for all the filters and parameters in the convolutional layers, and random values are also assigned for the weights and bias values in the fully connected layer. Then, like always, the network receives an input. In this case, it receives a training image, which goes through the length of the neural network. Its features are extracted with convolutions and scaled down into abstracted representations with the pooling layers. And then, after extracting the necessary features, they are then classified thanks to the fully connected layer. As our network attempts to classify the image, it outputs a prediction such that malignant received the higher probability. This outputted prediction is compared to the target prediction, the label, and supposedly this image corresponds to a benign breast lesion. It's not malignant. It made the wrong prediction. The overall error, the cross-entropy value, is calculated, and it turns out the error is quite large. And so to minimize this error, we must update all the filter values, the weights and bias values of our network. And once again, this is done using backpropagation, where we still use gradient descent to update the parameters in the network based on the gradient of the error. It's interesting, we still make use of gradient descent. And after minimizing the error, eventually the network learns the proper filter and parameter values to correctly extract features and classify them accordingly, ultimately outputting the correct predictions for the image. The values of the filter matrix in the convolutional layer and connection weights in the fully connected layer are the only things that change during training. But as far as the number of filters in the convolutional layer, the kernel size, the number of convolution and pooling layers, none of that changes during training. This is something we have to specify early on once we put all of this into code. Regardless, I hope you can see that training a convolutional network is very similar to how we previously trained regular deep neural networks, in the sense that you start with a random parameter and filter values, determine the error, and then backpropagate the gradient of the error to update the parameters in the direction that minimizes the error the most to come up with a model which learns to classify the training data correctly. This concept should seem familiar, and we won't cover the mathematical operations this time behind the whole training process, since I want to start applying all the theory we've learned into code. In fact, for now, that's all we're going to cover for the theory behind convolutional neural networks. We could go on forever and talk about padding, strides, various convolutional architectures, dropout layers, which we'll come back to eventually, but for now, we know enough to stop and start putting all of this into code. I will see you there.